Where are you in space at this exact moment? Most would say the obvious, maybe sitting down at work or home, maybe listening to this while driving. But this is a surprisingly difficult question to answer given the more precise you want to be. Ungodly amounts of money and time have been spent trying to pinpoint the location of people, vessels, and spacecraft for as long as we've been launching satellites. But why does humanity invest so much into precision locating? Well, here on the surface of Earth, things only move as fast as their engines can take them. But in the greater universe, where all of our costly geopositioning satellites and planned or executed deep space missions take place, the universe is flying past you in all directions at thousands of miles a second. How do we know exactly where we are in a constantly shifting and high-velocity universe? Welcome back to Sirius Science, and these are what our descendants may use to light their paths through the infinite void. Before we begin, subscribe if you enjoy this kind of content. I may have been on YouTube for more than 5 years, but I'm still learning more about the platform. Apparently, liking a video makes it appear more in the algorithm, so if you think it deserves one, go ahead and give it a like. Yes, I hate these sections too. Why is knowing your position important in the first place? The most well-known examples of this are GPS satellites that nowadays can give you extremely accurate location information. This is of course useful for mapping programs that give you directions to other locations, keeping track of ships hundreds of miles from land, aircraft as they navigate available routes and avoid locked ones, and even how many of our devices tell time. The main method these satellites use to determine the position of a device or object is through radio waves that link up with other satellites and triangulate the position of a tracked object based on how quickly those radio waves hit specific satellites. The microscopic time differences measured between these satellites, which are all orbiting at different heights or speeds, is measured against how quickly that radio message arrived. These arrival times can differ by fractions of milliseconds, and the more accurate of a measurement we can take, the more accurate your position can be tracked. These differences are small on a world where most everyone lives on the surface, but when we start tracking probes or manned missions traveling far beyond the influence of Earth, more challenges are introduced. While satellites traveling at many miles per second may prove difficult to track or relay data without timing losses, they all do so with respect to the world that turns beneath them, and have few otherworldly targets they need to keep track of. To them, the Earth is at a set distance from them, along with everything they need to keep track of on the surface. But as that view expands outwards, everything begins moving far faster. The Earth is spinning at a rate of 1,000 miles per hour, while also traveling around the Sun at 67,000 miles per hour. But the Sun is also moving through the galaxy at 498,000 miles per hour, and the galaxy itself is traveling at 1.3 million miles an hour. And the universe is expanding at a seemingly inconsistent rate, and all of the stars in our galaxy are flying around all the other ones, and those stars are all gravitationally changing all the other ones that they fly past, and, well, there's the issue. If we want to keep track of an interstellar ship, let alone many of them, all while flying through a cosmic demolition derby of immense masses and gravitational influences, we will want to be aware of as much of that motion as possible. So while here on Earth these speed differences are almost negligible, we need to keep in mind that a possible speed difference between us and a target may be measured in the millions of miles per second, which will also register in the Doppler Effect, which will skew our data even further. The fastest possible method of data transmission we currently have is using the fastest possible medium in the universe, that being light waves like radio. But light itself can be affected by speed and gravity. If I'm traveling away from you at a few million miles an hour, the light I reflect or transmit will appear stretched to you, called redshifting in astronomy, due to the light from distant and fast-traveling stars often appearing redder than how they should, due to the light they give off becoming stretched into a lower energy wavelength as their speed away from us increases. This is true in reverse as well, where stars traveling towards us will appear more blue, and their light waves will become compressed, appearing as a higher wavelength than what the star actually outputs. Light can also be affected by gravity, as high-mass objects like stars or galaxies will actually bend passing light around them, changing the apparent position of whatever we want to track, as well as shifting the light that object gives off like a prism of gravity. The Doppler effect will also skew our transmissions, and if we are receiving data from a distant probe affected Affected by this shifting, the data will appear imprecise. These aren't new issues to space exploration, and a good example of how much the simple act of traveling quickly can pose transmission hazards is with the Huygens probe mission to the surface of Saturn's moon, Titan. It was a detachable surface probe that left its parent probe Cassini, and was designed to aerobrake in the atmosphere of Titan much like how a Mars probe would, with a heat shield and parachutes. But the entire mission to Titan's surface was almost a failure when a crucial flaw was discovered after the mission had left Earth. Keeping track of Cassini while it shot past both Jupiter and Saturn, then as it flew past many of Saturn's other moons, was already a challenge due to these gigantic bodies steadily changing the speed of the probe, affecting how stretched out the data we received from the probe became. But the largest issue with the Doppler effect came with the separation and landing of the Huygens probe. The method of data transmission the probe used to relay with the Cassini orbiter used time pulses to distinguish where one string of data ended and a new one began, essentially acting as periods in between the sentences of information. These pulses were crucial in decoding the data sent from Titan's surface, as if these pulses were absent, the data would become unreadable, and the mission would have been a failure. But how would a probe lose track of an object falling onto the surface of a body it was flying past? Wouldn't this be another example of talking to a satellite we have here orbiting Earth? Not quite, as it all has to do with frequencies and the Doppler effect. Most methods of transmission we use today are focused in on monitoring specific frequencies. As if they allowed more than that one frequency in, the data would become noisy from all the other radio frequencies being received. But this one issue had been prevented during the early design phase of the Cassini mission. As the detachable Huygens probe began to enter the atmosphere, it did what it was designed to do. It slowed down. This slowing of momentum in the atmosphere would pose a significant Doppler issue, as its speed relative to the probe would drop by about 5.5 kilometers per second, a very noticeable dip in transmission frequency. If the orbiting probe could only receive data in one specific frequency, the slowing of the probe would have just shifted it into another unreadable frequency, preventing us from monitoring it as it landed and transmitted data back home. This, coupled with the precisely timed separatory pulses Huygens transmitted to make its data readable, would have become unrecognizable to the probe, as the pulses would become shorter and unnoticed by the decoding program, scrambling the data during the most crucial part of the mission as the lander fell and made measurements. Luckily, rocket scientists are far smarter than I, and an algorithm was developed that would narrow the bandwidth of the receiving antenna on Cassini timed to the expected descent of the probe, essentially shifting the expected frequency with that of the probe as its speed shifted the resulting signals, a slow tuning of the dial as the signal shifted. As a result of their brilliance, we now have exquisite data of the surface of Titan, including images as it fell and landed, sounds of the roaring winds, atmospheric makeup, and surface composition. Despite the Doppler issues, both expected and unforeseen, the mission was a success, but illustrated just how much of an issue transmission stretching was even on the scale of a single moon around a distant world in our own solar system. How can we transmit data both to and from an even farther object that may be following another star or even the edge of our galaxy, when that star may be traveling far faster than a few kilometers a second and not in a straight line, which would gradually change the Doppler effect as it orbited closer to or farther from Earth? Plus, that transmission will have passed through dust clouds and past gravitationally dense stars that shifted its direction and frequency. How could we eliminate or account for these minute but still destructive changes at interstellar distances? How could we keep track of thousands if not millions of other ships, probes, surface bases, and orbital stations, all spread throughout the galaxy and all traveling at different speeds relative to each other and Earth? Well, if we want to be able to reliably transmit routes or new info to our interstellar travelers, we will need to do so on a case-by-case basis, perhaps including a specific identifier data stream in their transmission, revealing their current location and speed that could be synchronized to the frequencies we are receiving from that ship here on Earth. A brief introductory string of data could be sent first as tuning instructions in order for the rest of their data to become readable, as a ship orbiting another star will be a better judge of that star's speed and conditions than a radio telescope aimed at that star from Earth. While radio communication has served us well on missions within the solar system, those waves can become severely affected when passing through a medium like gas or dust. The Doppler effect applies to really any and all transmission methods, as no matter what we are sending, even if it's a string of particles, will be affected by their speeds and your own. But this isn't to say we cannot develop other methods of transmission that would be unaffected by passing through clouds of gases, and one of them we may be able to detect even if it had passed through a planet. Neutrinos are truly fascinating. They are subatomic particles with masses as close to zero as we can get without becoming photons, traveling 99.99999999995% the speed of light. They are neutral and tiny, meaning they very rarely interact with the matter they pass through or past. Neutrinos from the Sun have been detected on the opposite nighttime side of Earth, passing through the entire planet without touching a single atom. Neutrino transmission has actually been tested here on Earth, when scientists passed a simple message straight through several meters of solid rock, and was detected strongly and accurately on the other side. While this method will also experience the Doppler effect, it will eliminate the issues we regularly expect with interstellar transmissions, that being their diffusions or scatterings as they pass through space, which is not at all entirely empty. But even this method will give a weaker signal as the neutrinos travel to farther destinations, much as we experience with radio waves. The farther an object we want to talk with is, the more diffuse the signal will be when it arrives due to the radio's or neutrino waves expanding outwards from the transmission point. One way around this issue of distance that we have developed is the use of highly focused and energy-intensive laser bursts of communication data, designed to keep a powerful burst of detectable information as tightly packed together as possible, narrowing but not entirely eliminating the spread of that data. This of course adds an additional problem of mass messaging, as that laser will only be picked up at very specific locations in space, and will need to track that position relative to the speed of the two parties. But what is the current best option for interstellar messaging? Well, it entirely depends on what we want to transmit. If we want to construct a probe whose purpose is to give positioning data to arriving or departing ships, we may implement neutrinos with preliminary data denoting its speed and surrounding gravitational conditions in a wide radio-like spread, traveling through a star or planet they may be orbiting to give a specific locational coordinate. Ships arriving in systems or trying to find them to set up a route will receive info about the destination speed and possible gravity deformations in the data before receiving a pulse of specific frequency allotted to that specific probe, all of which could be done with a simple string of data. If we want to transmit a large amount of data to a ship, like a software update or video of another world, the laser transmitter will be best suited, as it excels in sending powerful and directed bursts of high bandwidth data with the least amount of corruption. These laser bursts will be undetectable to anything they weren't pointed at directly, but would accomplish high-intensity data transmission the best compared to our other methods. But what if we wanted to transmit a strong signal to every corner of the galaxy to denote a place of importance or heavy traffic like Earth may become as it communicates with interstellar ships and settlements, a set and powerful beacon lighting the way home? While I wouldn't recommend taking the Emperor's approach and lighting it with the power of consumed psychic souls, the beacon will still need a tremendous amount of power to allow for its most distant receivers to pick up anything stronger than cosmic background radiation. An orbital installation powered by immense nuclear or fusion reactors could output terawatts of transmission power, reaching out to even other galaxies, and could be set up in the orbits of human-occupied worlds, all set to their own bandwidth and frequencies, being constantly adjusted to give a universal baseline of frequency as the transmitter changed speed and direction with respect to Earth. If we use neutrinos, we could burn these beacons brightly even while behind stars or planets, accounting to how the gravity of those bodies would shift the transmissions passing through or around them. Gravitational lensing may be the more difficult issue with interstellar beacons, as nothing we know of is unaffected by gravity. This makes more sense when we recognize that all methods of transmission travel through space, and space will bend around heavy objects. In order to be detectable to creatures living in space, they will need to travel through space, which is ironically something we want to limit our transmissions from interacting with as much as possible. No known material or wave can do so completely unaffected, just to a lesser degree in the case of neutrinos. Lensing can distort a message just as much as the Doppler effect can, and the prismatic scattering due to speed differences also applies when that message is bent around an object, causing the message to shorten or elongate. The most intense example of how lensing can distort light waves can be found around black holes, the seeming ultimates of the universe, and even points towards possible methods of infinite energy production. As light passes a black hole, the massive gravitational sink will bend the light around it, of course, but will also change drastically if it passes close enough to the event horizon. As this light shoots past, it will become intensified, as light cannot be accelerated to speeds faster than light. It will instead intensify its wavelength. Therefore, radio waves may emerge as microwaves. Red light will become more blue and higher energy. If we were able to entirely englobe a small black hole, a far easier task than surrounding a star, as black holes can measure in mere meters instead of thousands of miles, we could beam high-energy light waves such as ultraviolet or X-ray directly past the event horizon, which will give them a boost in energy intensity. We could do this multiple times if the interior was mirrored against ultra-energetic waves, which we still have no idea how to do with a 100% success rate. We could expend a small amount of energy and harvest a far larger amount as collectible light frequencies, essentially throwing a canister of gasoline past a black hole and receiving an additional canister back, doubling the energy we put into it, all due to the massively intense warping of space-time. Such methods may even be implemented in transmissions as well. If we wanted to communicate with a destination on the other end of the galaxy and cannot provide enough power to do so reliably, we may pass that transmission past a black hole to intensify the wavelengths, attaching a string of introductory data that could account for the warping of such a method as to be decodable on the receiving end. But these beacons could also serve another purpose other than the pure transmission of data. The issue with monitoring a distant star comes from all stars not being the same. Our own sun is a particularly massive and strangely docile star, one whose assumption of normality by us has often skewed the expected data we have received from others. Stars can change their outputted light at random, can become hotter or cooler sporadically, and show other signs of instability or seemingly random change. This makes them difficult to learn more about, as you very well could set your sights on a star and discover it has changed dramatically while you were en route, appearing as a different star entirely. We could set up these ultra-powerful transmission beacons around said stars that could monitor their changes directly and send back data tuned to a cosmic baseline, providing data on the star's instability from close by instead of us making guesses at many thousands of light years apart. This way we could determine if they were suitable for habitation or were close to a catastrophic burst of dangerously high energy. We could even set up these beacons to monitor the deaths of stars we wanted to be as far away from as possible, as when those novas occur they can vaporize anything between a few million miles to several light years of destruction in the case of supermassive stars. We could monitor the Doppler effect of these beacons to reveal gravitational changes as the stars explode, the kinds of light they give off as they die, and even the elemental makeup of these stars as those materials impact and change the speed of the orbiting beacon at a set rate due to their masses and measured speeds relative to the beacon. This isn't to say our interstellar beacons will be simple transmitters and receivers, as they could be stocked with everything we envision a futuristic space probe to carry, complete with powerful telescopes, elemental capturing and processing experiments, all manner of scanning and spacebound equipment, and perhaps even equipment for the eventual colonization of that location should it be found suitable. Indeed, these beacons could be attached to probes sent to other stars, activating to send immensely powerful data streams back home and staying as beacons once their exploratory mission had been completed, marking their place on a constantly shifting and warping map. Most of this video has been talking about the methods of transmission and how to circumvent possible issues of using certain mediums, but I want to also include a brief section on why exactly setting the beacons up would be beneficial. A simple orbital satellite that can send messages to the other end of a star system will undoubtedly be one of the most prevalent machines we would use to communicate. But once humanity has spread farther than a single star, we will need these transmitters to be as powerful as possible, necessitating the construction of large and energetic facilities with the single purpose of transmission relaying. But why would we want to use these to keep track of every ship possible? Doesn't that sound a bit Big Brother-esque? Well, not at all, as they wouldn't be gathering any more data than positioning and relative speeds. And we employ a very similar GPS system here on Earth for far more than just spying. Spaceships are incredibly complex machines that need to withstand incredible amounts of heat. G-forces, aeronautical pressures, and perhaps even deadly and corrosive atmospheres if they were designed to make a landing on a place like Venus. With all of these constant stressors on our ships, things will undoubtedly begin breaking down, possibly in a catastrophic manner. Today, we still lose aquatic ships to the immense forces of the ocean, and needing to know exactly where a ship has become stranded or sunken is vital to any rescue effort. While an interstellar ship traveling 20% the speed of light that breaks down halfway through the trip will need many decades or hundreds of years of travel at a significantly higher speed to reach them, rescue efforts can still be mounted if that ship were able to stabilize itself outside of making those crucial repairs and spend the rest of their trip doing what they were already fully equipped to do, waiting long periods of time. If we want any shot at reaching these stranded colonists, we will need to know their current location and rate of speed in order to find a possible rendezvous point. The immense distances and relative speeds of our ships will mean that any rescue effort will need to be made on both ends, as immediate rescue even within a week would be almost impossible without instantaneous travel or FTL devices. A stranded ship must be able to somewhat stabilize their situation in order to survive long enough to be rescued, which could be anything from a simple deployment of an SOS signal to welding enough of their tattered ship back together to hold the remaining crew in stasis long enough to be discovered. While ships already inside a human-occupied system will have the best chances and rescue times compared to the rest of the universe, the ones that break down halfway to or around an alien star may be discovered many hundreds of years into the future, completely desiccated and destroyed, even if an initial rescue beacon had been deployed. Such are the issues with space travel. The speeds and distances become inhumanly immense. But these possible fatalities may also present the need for our hyper-powerful beacons by way of an avoidance signal. If a ship becomes totally disabled while traveling at significant percentages of light speed, it is now essentially a hypervelocity warhead and will completely decimate anything smaller than a planet if it impacts. It may even become fast enough to act as an extinction-level threat to any planet in its way, similar to the already prevalent planet-killing asteroids that fill space. These kinds of debris clouds traveling at these immense interstellar speeds will be high-priority targets we would want to keep track of, and a powerful warning beacon may be inserted into the debris cloud in order to fly alongside it as it makes its way through the universe, if we couldn't entirely collect all of the pieces of the destroyed ship, which may have been a vast colony ship measuring many miles in length and weighing in the millions of tons. These beacons could act as warning signals if these debris clouds begin nearing an occupied system, instead of the current systems we have in place for tracking hypervelocity debris around our own world, which rely heavily on estimation and how small of a target we can track from the ground. But there may be one last use for a wide network of powerful beacons that would prove a more exploratory function. I want to impress upon you two ideas that I've reached while learning about the universe. Sometimes it seems we know so much about space, from how stars form or behave to the age and width of observable creation. We know Mars once had oceans and that gravity travels in waves that we can detect, and that matter is made of atoms, made of particles, made of quarks, possibly made of strings that vibrate through subatomic dimensions, and far more wonderful things than I could ever recite within a lifetime. For many thousands of years, we have been endlessly learning about what we are, where we are, what we are made of, and everything else you can imagine. More often than not, these answers only bring more questions to be explored, like how the discovery of glass optics led to the discovery of microscopic life through newly developed microscopes, which were developed after someone had wondered what they would have seen through a reverse telescope aimed at the mundane instead of the celestial. This is the first idea, that we know so many incredible things, yet have no idea what we will find out in the wider universe, maybe even the smaller ones. It still leaves us with important questions and adventures to go on, if not for the simple desire to understand and wonder at something you can truly call new to humanity. The second idea is the inverse of the first. I want you to keep in mind all of the incredible discoveries and the ones you can personally remember and realize this. These were all made from one vantage point on the surface of a single world, Earth. Whatever wondrous discoveries we have made were entirely based on what the universe could show us from our single vantage point, a single planet, through a single atmosphere looking up at the same stars that aren't blocked by our galaxy or other stars. There are vast shadows in our vision, ones that will need to be circumvented to get a clear, unobstructed view of the universe. The second idea is that while we know so much already, it has been everything we've managed to squeeze from the one planet we have ever visited. If we can deploy many hundreds of thousands of beacons all throughout whatever stars we could reach, they would have prime positions to observe truly remarkable processes. From how planets develop and perform for cosmic amounts of time, to orbiting exploding stars and transmitting their findings from within powerfully enough to scream above the messy noise of stellar decay. Even the simple act of monitoring radio wavelengths may enlighten us to new processes in the wider universe, and can more accurately triangulate the positions of strange or unexplainable signals. They could also relay and amplify non-artificial radio bursts for clearer reception on our worlds, holding the microphone directly to the event instead of setting it up light years away. They could act as a billion new eyes and ears connected to the greatest minds of humanity, using as much power as we could pump through them. Even when compared to the kinds of probes we would envision building to do such tasks, those probes will be quite distant from any powerful receiver, and may need to come equipped with these necessarily massive transmitters anyway, with a significant portion of their mass dedicated to relaying, powering, and receiving our faint messages. For any of the messages we will want to send to one another across the universe, doing so as loudly and as powerfully as possible will be the priority, no matter what method is being used. To do so will require both large and powerful transmitters, as well as further discoveries on perfecting the equipment. But in this possible vision of the future, humanity will shout loudly and clearly to one another and to any other possible listeners, even from galaxies away. Uniting intelligence through communication may not even stop at the species that made it. I hope you all enjoyed, and thank you very much for watching.